All right, so we're going to do two things today. One, we're going to finish the proof of ideals factoring uniquely as a product of primes in the integers of a number field. And then second, I'm going to give you an introduction to Sage and answer questions about Sage. And just because projectors often take a long time to turn on, I've attempted to, let's see if this works, start this one early. Does not look right. But first, while you're waiting, try to remember everything from the proof that prime ideals are invertible as I prepare this, because I'm going to just begin right immediately, assuming that you remember the proof from last time. So that would be good to have in your head. Okay, I'm not going to use this until a minute from now. Okay, so very, very quickly, recall from last time that we proved that if you have a prime ideal P, so the general statement that I made was that if you have a prime ideal P that's non-zero in the ring of integers of or in a Dedekind domain, then it's invertible. What I'm proving is that if you have a prime ideal P in the specific Dedekind domain, the ring of integers of a number field, then it's invertible. And so I did that last time. So here P is a prime ideal, and I proved last time that if you let P inverse be the set of elements A in K, such that A times P inverse is contained in OK, then you have the product of the following two fractional ideals, P inverse times P is equal to OK. And this was the first step towards proving that the set of fractional ideals in a Dedekind domain is a group. Any questions? What did I write?
P inverse.
Oh, that doesn't look good.
Recursive definitions, no good.
That would not be good. It would be recursive and then that would crash, or you would. So I'm glad you're all human and not computer. This lecture would have blown up. Okay, so here we are, we have this so far. So now what we need to prove, the next statement, I mean it's all well and good that prime ideals are invertible, we need every ideal to be invertible in order to have a group. So here's how we'll prove that. We have an ideal I, and it's just an arbitrary ideal now in OK. If it's a fractional ideal, you can multiply through by a scalar, a non-zero scalar, to make an integral ideal, and then prove something for that, and then you'll recover what you want easily for a fractional ideal. So let's assume it's an integral ideal. Now, let's use that OK is a Noetherian ring. So that means if we take the collection S of all ideals that are not invertible, then it has a maximal element. And we might as well assume that this I is such an element. So I is maximal in the set of all ideals that are not invertible. Okay? First, I is certainly not itself a prime ideal, because if I were a prime ideal, it would be invertible, since we just wrote down and proved that prime ideals are invertible. So I, being an ideal in a ring, in a commutative ring, is contained inside of a prime ideal. So let's just stick that in here. There exists some prime ideal P that contains I. This P, quote, divides I in the notation from yesterday. So now let's consider I, which is contained in I times P inverse. This is just because P inverse clearly contains OK in the definition. And then this is actually contained in OK. So you have that chain of inclusions. The last one is because this I is contained in P, and when you multiply P times P inverse, the result is contained in OK. So certainly, I times P inverse is going to be OK, since I is a subset of P. So you have this. If it's the case that this guy, IP inverse, is not equal to I, we're set, because it's something that's bigger than a maximal element of a set of things that don't work. And it's invertible. It has an inverse. So as long as you don't have equality here, this guy has the inverse J, and you have IP inverse equals J, so I equals PJ, and you're done. So all we need to do is show that this is not an equality. We just need to show that this inclusion is proper. I is properly contained in I P inverse. Okay? That's all we need to do. Because once we do that, we use that I was chosen maximally, then we know that I P inverse has an inverse, say J, and then you multiply both sides by P and you get that I is equal to P J, but, well, actually, more to the point, I P inverse equals J and J has an inverse, which means that I P inverse times this thing J inverse is okay, and then just by associating, you see that I times P inverse J inverse is okay, therefore I is inverse. Okay? So, any questions? So all we need to do is show that this isn't equal. But that was exactly the trick I showed you last time at the very end. If it were the case, if I equals IP inverse, then just imagine taking each element, taking any element of P inverse, you can write it with respect to a basis for I as a Z module, you can write down its matrix. Its matrix has integer entries because it takes I into itself. So any alpha in P inverse has an integer matrix. It's representable by an integer matrix. With respect to some basis for K, namely the basis, take some basis for I. So with respect to a basis for I as a Z module. Remember, well, the key thing I'm using right here is that I, it's an ideal contained in OK. It's a non-zero ideal in OK. And remember that I proved that every non-zero, well, remember when I proved that every non-zero prime ideal is maximal? The same argument gives you that this I has finite index in OK as a module. All you do is you take some non-zero element of I, you write down its minimal polynomial, you look at the constant term, that shows you that there's an integer in I, and then what you have is this, and NOK has finite index in OK, therefore I does. So this I has finite index in OK, so if you take I as some, think of it as a subgroup of the number field under addition, if you take the Q span of it, it's just equal to K. So you just choose some basis for I as a Z module, that's also a basis for K. Write your alpha as a matrix, the map multiplication by alpha as a matrix with respect to that basis. Since it preserves I, it's actually a matrix with integer entries. You can just try this in any particular example. It's a matrix with integer entries. Therefore, its characteristic polynomial and hence minimal polynomial is a polynomial with integer entries and monic. It's a monic polynomial with integer entries. So alpha is integral. And that means that it's in OK. So alpha is in OK. But the fact that alpha is in OK tells you that, well, this is for any alpha P inverse, that tells you that P inverse is contained in OK. And that means that, that's impossible because if P inverse is contained in OK, then you have P inverse P contained in OKP, which is equal to P. But on the other hand, it's equal to OK. It's ridiculous. So there's no way you can have P inverse being contained in OK. It just wouldn't work. P inverse clearly contains OK from the definition, but it has to be a little bit bigger. So you get a contradiction if you assume that I is equal to IP inverse. Therefore, I isn't equal to IP inverse. Therefore, this IP inverse thing is a little bit bigger than I, and that makes it invertible, because we're working with a Noetherian ring, and we know that we can do that. So that makes this invertible, which gives us an inverse for I. So we've now proved every non-zero ideal has an inverse, which means that the collection of fractional ideals is a group. Okay? So now we have a group. Any questions? I'm going to give a proof now that every ideal factors uniquely as a product of prime ideals. And the proof is going to be shockingly similar to the proof I just gave. So if you didn't quite get this one, you'll probably get the next one by way of redundancy. Okay? So we now have the statement that each ideal has an inverse. And we got it really pretty formally just by using the properties of a Dedekind domain plus this one extra trick about integrality. So finally, our big theorem is that every I in OK factors uniquely as the product of prime ideals. This is not subset, this means non-zero ideal. Factors uniquely as a product of primes. Okay, so can you guess what the first step will be?
Take the collection of all that don't.
Yep, take the collection of all that don't, take a maximal I that doesn't. Here it is. Okay? And now, as before, either if I is a prime ideal, you're done, because of course it factors in, well, it factors as a product of primes. I'll worry about unique in a second. So it's not prime, therefore it's contained in a prime. That's contained in OK. And gee, let's do exactly the same thing as we did over there. I, P inverse contains I, and this is contained in OK for exactly the same reason as before, because, well, let me explain that. So I is contained in IP inverse is contained in OK, and if this is bigger than I, if IP inverse is bigger than I, then we're in really good shape, because that means that this can be written as a product of primes. If this is a product of primes, you just multiply both sides by P, and you get the I as a product of primes. So the only problem would be if I equals IP inverse. But it doesn't, the reason is identical to what I wrote here. Or if you believe the argument I gave here, if these two are equal, since we're working with a group, you could just cancel the I from both sides, and you get that P inverse is equal to OK, which is of course wrong, because P inverse, if that were equal to OK, it wouldn't work. P inverse would not be an inverse for P. So you do not have equality here. Hence, this is not in the set of all ideals. It's an ideal, but it's not in the set of all ideals that don't have a representation as a product of primes. So we get from that that I, P inverse, is equal to a product of primes. And now, again, we're working with the group, so you can multiply both sides. You get that I equals P times P1 up through PQ. Okay, so I've now shown that every ideal has a representation as a product of primes. Finally, the very last thing is to show that this representation is unique. So suppose it isn't. Suppose we can write this as Q1 dot 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 QS. There's a different representation. Now all I have to do is show that at least one of the primes matches up, and then I can cancel from both sides and repeat, and we'll end up seeing that, at the end of the day, we'll end up with the unit ideal equals a product of primes. And a product of primes is contained in any one of those primes, which would be a contradiction, so it has to be an empty product. So now all I need to do is show that you can match up something on each side. That, well, just to fix ideas, let's show that one of these over here, one of the P's, is equal to Q1. Okay? If we show that, then you can cancel since we're working with the group. So here's the trick, and you've actually seen this trick before many times as well. I'm going to show that Q1 is equal to some Pi. To show that, because I'm working with a Dedekind domain, I just need to show that Q1 contains one of these Pi's, one of the things on the left. Let me call this one P0. So I can say Pi. So suppose to the contrary that none of the Pi's on the left is contained in Q1. Then for each I, you can choose an AI in Pi that's not in Q1. Okay? Now take the product of all these AIs. It's in the product of these ideals, hence it's in here on the left-hand side. So the product of the AIs is in there. It's in the left-hand side. Hence it's in the right-hand side. But the product is divisible by Q1. It's contained in Q1. Because ideals, if you take something in Q1 and multiply it by a bunch of other things, it's still going to be in Q1. So this AI, it's a product and it's contained in Q1. But Q1 is a prime ideal, and prime ideals have the property that if any product is in the prime ideal, then one of the factors has to be in that prime ideal. And that tells you that you have a contradiction, because I chose the AI so that none of them are in Q1. So we have a contradiction. You can't do this. There has to be at least one of the PI's that's contained in Q1. But we're working in a Dedekind domain. Every non-zero prime ideal is maximal. So in fact, one of the PI's is equal to Q1. So let's just say it's this one right here. So you can cancel them because it's a group. So you just continue canceling in that way, doing this over and over again, And at the end of the day, you end up with a product of primes. Let's say maybe could be P2 times P7 is equal to the unit ideal. So that's what you get at the end after you cancel as much as possible. As long as you have something on both sides, you can always cancel. But there's no way you can have something like this, because on the left-hand side, you have something that's contained in a prime ideal, and on the right-hand side, you have the unit ideal. So you get a contradiction. So that proves uniqueness. Yes?
Just an alternate proof idea, and I just
Sure.
wondered if it's working on. Could you just invert all the elements on the left? Multiply times all the PI inverses on both sides, and then
Good.
just have a product of things equals.
Yep. The problem with that, the worry there is you have a whole bunch of inverses. So they're actually not integral ideals. They're fractional ideals. So you have a product of a whole bunch of things, but they're fractional ideals. And so you could easily have a product of a whole bunch of fractional ideals that's equal to OK a priori. You can have P1 times, say, P1 inverse. These are two different fractional ideals, but the product is OK.
Right, but the proof would just
problematic.
be like you have none of the like therefore because you have to have it be like that because you use a group structure. Therefore, one of the
No.
QI has to be.
I think that's kind of circular.
It
Because for all you know, couldn't it be that, let's see, is that circular or not? I mean, how do you know there aren't some relations? You know that, I mean, how do you know that P1 times P2 isn't equal to P3? How do you know something like that doesn't happen without an argument like I gave? The group, just being a group doesn't give it to you. In fact, we're going to work a lot with the class group, which is these ideals modulo a certain equivalence relation, and then you do have all kinds of relations, and you're still working with the group. So I don't think that argument works directly, though I'm sure that you can make it work with sufficient modification because you're proving something true. Yes?
So we've switched from just general Dedekind domains
Yes.
to OK. Is it
Yeah.
true?
Yes, it's true.
But
But the proof, the only thing I'm using is this little trick involving integrality,
yeah.
and there are ways to get around that in general, which I'm not going to go into. I don't remember them off the top of my head. Well, I'm using that in order to get it to OK, but I need to know that if I equals IP inverse, then basically I need to know that if an integral ideal is left invariant by an element, then that element must be integral. Okay, so that's a statement, and it's true in general. And if you prove that, then you would have everything I said in a general Dedekind domain. And it is true, but I'm not proving it. I'm only proving things because it's really easy here since you just take a z basis for I. Yeah, and I'm also using that every ideal, when you quotient out by it, you get something finite, so that you have finite index. That's not true in general for a Dedekind domain. But still, the conclusions I'm making, except for those things, are true. Like, for example, C adjoin X, the polynomial ring. That's a Dedekind domain, but there's ideals, for example, the ideal joined by X, where when you quotient out, you get something that's uncountable. So I strongly encourage somebody to look up and quickly understand how to get around the issue of this in the case of a general Dedekind domain. And then on Monday or Wednesday, raise your hand and say, hey, I know how to do that. And then everybody will be happy. Okay? So somebody do that. It'll impress us all. All right, so any more questions about this sort of background about Dedekind domains? Okay, so that is chapter 3, I think I declared done. And the other two things for today. One, I'm going to redistribute the homework. I'm done grading it. Just kidding. So what's going to happen is I'm going to randomly redistribute the homework. If you get back your own homework assignment, let me know so I can redistribute it again. Then over the weekend, you're going to look over the solutions that somebody else wrote in the class. And you're going to go, that's a really nice solution, I didn't think of that. Or that just doesn't make any sense, or whatever. And you should just grade the homework. The way the grading works is that each problem has equal weight, and parts of problems have equal weight as well. So on homework, I guess 1 looks like there are 5 problems. So should I do that? We know about fractions. So how about each problem is worth 1 point, and then if you got 1 part, so the total you can get on a problem is 1 point. And so if the problem has 3 parts, then each part's worth 1/3. Is that okay? It's the simplest thing I can think of. And so you can get a total of 5 points on this. When I no, Well, of course. Well, I guess, yeah. I would prefer rational numbers for the grades because I do have to enter them in a computer. We don't have a packaging stage for transcendental numbers yet. Real Life didn't make it in because it only supports Linux. So, yeah, so I'll redistribute them, grade them, do the best job you possibly can. I know everybody here has probably graded papers before. And then return them on Monday. Oh, you don't have to grade if you're on. So return them on Monday, and then I will grade them. Oops. Here you are. And don't lose your homework that you're grading. So I did this grading method with undergraduates last quarter, and throughout the entire quarter, not one undergraduate lost another person's homework. So if they can do it, if they can do it, you can. Dustin, do you want to make any comments since you're the official grader for the undergrad course after the students graded each other's homework? So I don't know if you want to make any comments on that.
You said this before, but when you say I did it and say write down the code that you used.
Wait, hold on, because he's talking. Sorry.
So if you say I did something, say write down the code so that someone else can check that you actually did it, and say you don't just say it. And if you take points off to explain why, if you don't understand something, write I don't understand, and then Dr. Stein can look at it and he'll feel really graded or something like that. But don't just try and guess or do something that you don't know, I'd say.
And I mean, one of the goals is that by reading somebody else's solutions, you'll get a better sense of how to write solutions that anyone can understand. And you think about it, every time you write up a solution, your target audience isn't just me, it's a random student in this class. That's who you have to convince of your solution first. Okay? So that gives you a good sense of who you're writing for. All right, so now on to the second part, which we have 25 minutes for. I'm going to give you a brief introduction to Sage. And let's see. Oh. Just trying to figure out how to get my laptop into the same place as me. By the way, this is Craig Citro. He's a grad student of HEDA at UCLA. He's here for a day because he won an award for the best collection of books about Arden, or written by Arden.
Just book collecting competition, but my collection was about Arden.
Just kind of a strange thing to win. It's in Seattle, I guess. There's a book award. So he gets cold hard cash for buying math books and collecting them. So,
yeah, they pay for my trip and actually my girlfriend's trip as well because we're staying at her parents' house. No.
And then the mysterious person on Wednesday was my brother, who was sitting over there. So there's always a mysterious visitor. Okay, so this talk will be, this is going to be basically an introduction to Sage. There are two parts. I think I won't even begin the second part today because of lack of time. So that means I'll do that on Monday. So first of all I'll do is give you kind of a big kind of overview of Python and Sage and what they're useful for. Basically, the goal is to explain to you how you can improve your efficiency and ability to do math research. And if you're watching it all with sort of what's happening with the NSF and funding and so on, you'll see that computational math is somehow becoming really, really trendy right now, which is kind of cool because at least when I was in grad school, anytime you sort of came near a computer and you're doing computation, people would look down on you. And, I mean, it really felt like it was bad or something, and that you were just being, I don't know, there was a lot of sort of discrimination against people who used a computer to do math, but it's suddenly turning full circle very quickly, and now it's sort of the trendy thing to do. In fact, I got an email from a guy who's on the job market for a tenure track position named Bill Hart today, who's been looking at the sort of jobs that are available. He's one of the Sage developers. He's a very sort of computational number theorist, and he was really surprised. He expected the job options to be really bad, and for his sort of unique skill set. And he was shocked because he said that there were at least 30 good positions that looked like things that he could apply for, and they really wanted somebody in computational number theory. So it is, for better or worse, getting really trendy right now. I see computation in math as basically, you have all possible tools for trying to prove a theorem. This is one more. And computers are clearly very powerful because if you just look at the influence they've had on society over the last 60 years or 70 years, it's profound. So not using them in math research is kind of stupid. Okay. Computers are also frustrating, but still. So Python, I don't know how many people here have ever heard of Python? Okay, good. So most people have heard of Python. It's a programming language, kind of like BASIC or C or C++ or Fortran or one of those many other languages, or Java or something like that. It's open source, it's free. It's been around since about 1991 or 92. It was developed originally by a guy named Guido van Rossum. His name is right here. He's Dutch, and he lived in Holland, and he worked at a lab that created a programming language where the whole situation was very hierarchical. Like there was one guy in charge, and nobody outside the lab could add new features to the language and so on. He was very frustrated with this, so he created his own language, which was designed to be very open. And so here's some quotes. So YouTube, they say Python is fast enough for our site and allows us to produce maintainable features in record time. YouTube uses Python a lot. Oh no, I need to put this in or something. I guess I can just. Let's see. Better performance. That's probably going to help. Okay, so Google uses Python a great deal, and for better or worse, Star Wars Episode 2 was rendered. Or Python played a big role in the rendering of Star Wars Episode. Huh. Well, switches do the same thing. So Star Wars is rendered using Python, partly. So what about Python? So Python is a language where it's easy to find your own data types and methods on those data types. So if you want to just make a ring, you just type class ring colon, and then you say what multiplication should be in addition and so on, and you get a ring. Or if you want to make a bit stream or a cipher or whatever. Python is a very clean language, and it results in easy to read code. So when you look at somebody else's code written in Python, you very often can read it, which is not the case with certain other programming languages, which is very much not the case with a lot of languages. So Python is good from that point of view. It's a little harder to write in some ways, at least initially, because white space is significant. So when you define a function, what happens is you write def, function name, the arguments, colon, and the body of the function has to be indented. Otherwise it's a syntax error. So it's not that you have curly braces or begin and end statements. Indentation actually has an impact on the meaning of the code, which is different than most languages. There are some languages you might have used, such as LaTeX, where white space does have significance, but most computer languages don't. Python does, but the good thing is that when you look at a block of code, two things happen. One, if it's indented in a certain way, the logic really is the way that the indentation claims, which is actually kind of nice because often code can mislead you with indentation. I don't know if you've programmed in C, you've probably seen this sort of thing happen before, where you go, that's something like a for loop, where you do something, and then you print something here, and then you maybe set some variable equal to the value of some function here. And of course it doesn't work at all, because if you don't put braces here and here, even though it looks like it's all going to happen inside of the for loop, it doesn't. So you end up with a bug. And you can easily end up with a situation like this by putting a print statement in here for debugging purposes. So you try to put a print statement in your C program, and you end up introducing a bug, and it becomes even more confusing. With Python, if you indent like this, that's the way it is. There's no way around it. But it's nice because it makes things more readable. It also eliminates all issues of where you put the braces, where you put end and begin statements. It makes the code cleaner. And you don't need semicolons at the ends of lines either. You don't need them. You can put them there if you want, but you shouldn't. It's generally considered to be an easy to learn language. What do you think, Robert? You learned Python recently. It's easy?
Yeah.
There you go. It's nice.
It's fun to learn.
Yeah, it's one of those fun languages. Some languages aren't fun, but it's fun. At MIT, they're switching from using Scheme for all their introductory computer science class stuff to Python, which I think will, hopefully it'll stay fun even though I don't know if there's some like karma where when undergrads are forced to use it, it's not as fun. But currently it's fun. Let's see. So there are a couple of free books to look at. These are just general books on learning Python. There's a huge number of libraries. It's, millions of people use Python, so there's libraries for statistics, networking, databases, bioinformatics, physics, video games, graphics, and serious math now via Sage. Sage, you can think of Sage as simply being a library for a Python library for serious math. There is actually a lot more to Sage than just that. You can use C and C+ libraries and also Fortran libraries from Python. And one of the things that's nice about Python is it has very good string manipulation and bit filling functionality. There's also a Python compiler that is something that can take most Python code and turn it into C code, which you then compile with the C compiler. And the website for that, cython.org, actually, oops. So here's the website for cython.org. You'll notice one of the main people behind the project is Robert Batchow's in our class. So we have really good support for improving Cython. So here's a quick history of Sage. We're actually
Turning off the light again.
oh, sorry about that. Thank you. So here's a quick history of Sage. So pre-Sage was 1999 to 2005. I used Magma a great deal, which is a commercial closed source program that is aimed at research mathematicians in very algebraic areas. And it's an extremely powerful program. It's completely different than Maple or Mathematica or MATLAB. It really aims at a much different target audience. And I think they have about maybe a little over 1,000 licensed users in the world. So it's a tiny, there are maybe 1/1000th of the number of users that Mathematica or Maple has. And so very, very tiny, but eclectic group of people. And they create a really, really powerful system. It's actually much better if you're doing serious math than say writing with C++, mainly because they have a library of functionality that's extremely good. When I say this, so it does a lot of stuff in commutative algebra, algebraic geometry. It does extremely fast basic arithmetic and exact linear algebra. And it has a huge amount of functionality for group theory and algebraic number theory and so on. So probably a huge amount of work has gone into it. So I used it a lot. I visited them 3 times in Australia, contributed a lot of code to their project, and convinced as many people as I knew to use it. Because it was really, really nice. But after a while, you start to realize that these languages like Magma, and also I think Mathematica and Maple, they are fairly old-fashioned and painful in comparison to Python. They haven't really changed at all. All 3 of those languages were designed in the early 90s. Python evolved a great deal since then. And these languages are very similar to how they were in the early 90s. They don't, especially with Magma, you can't define your own data types, you can't define your own classes. Doesn't even do, if you have a circular reference, if one object points to another and then it goes back, it doesn't garbage collect any circular references. It can be very painful, so it's easy to create memory leaks. It's difficult to extend those languages in C, so if you have a little inner loop in something that needs to be really, really fast, it's hard. And worse, the worst thing that doesn't really feel modern about those languages is that you can't look at the source code for anything, which really is the way things are going. So I was annoyed by that, and I really it started becoming increasingly clear to me, actually at the first Magma conference that I spoke at, that it's critically important to be able to actually look inside and change and improve on the implementations of code you're using if you want to be the best in the world at a certain research area that involves computation. So I remember, for example, this guy, Manjul Bhargava, who's a Princeton professor, who's actually a little younger than me, and he was a student at Wiles, and he was doing some research involving, I think, enumerating number fields or something, and he ran into a brick wall because Magma almost did what he wanted, but it didn't quite, and he couldn't change it. So he ended up writing this whole other thing just because of that. He was very, very frustrated, actually, that it was closed. I, of course, ran into the same sorts of issues. Less so personally because I had access to the internals, but other people didn't. So I decided Magma is a very bad long-term investment. And Then in February 2005, which was just under 3 years ago, I released the first version of Sage, which was mainly then a math library written in Python. And then I got a job at UCSD, so I moved, and they gave me money, so I ran a conference and got a lot of people interested in Sage. Until this point, for the first year, there were about 3 people, including me, who were working on Sage. So it wasn't a very big effort, though we were all working hard on it. So after this workshop, there were a lot more people working on Sage, and then University of Washington hired me away from UCSD, so I moved up here and had a second Sage workshop. And then Craig, who's sitting right there, pulled a few strings at UCLA and got funding for a workshop at IBM, which we had in March, and in fact we'll have another one I think in late January or early February. So right after this class we're going to brainstorm about how to write a grant proposal for that. And then we had another workshop here in, I think it was in May. No, it was in June. It says right there. So we had Sage Phase 4, and this was funded by the NSF Vigor PIMS thing. So it's like these graduate student workshops. So this was sort of meant as a graduate student workshop training type thing. So now the current version of Sage is 286. There are well over 100 contributors to Sage at this point. So a lot of people actively working on it. Typically when somebody asks a question or suggests that something isn't quite right in Sage, it used to be that I always answered the question and hoped maybe somebody else would look at it, and now there's usually, well, this morning I was trying to answer a question from one guy, Joe Muller, and by the time I finished typing it, there were 2 other answers below mine, so it was so there's a lot of people who are actively involved in Sage development at this point all over the world. In fact, in that instance, the guy who answered the question is a guy named Carl Whitty, who works at, I think, something called Newton Labs that does computer vision in Renton. He's not an academic, he's a guy who works in industry just south of here. And I've actually met him, I think, twice since, but he works very hard on Sage. He's incredibly good at anything involving floating point numbers. There was a workshop that I was gone from this class for in 2007 at the Clay Math Institute, which is a major player now in supporting mathematics at a high level. So they supported a workshop, which was very nice. Craig, you were there. It was nice.
Yeah, it was very nice.
Cool. And there'll be a workshop in a couple of weeks in Bristol in UK at something called the Heilbronn Institute. So that's coming up. So here's an example of Sage. You start it up and you can type 2 + 2 and you get a number. Probably, has everybody here at least tried Sage a little bit for the homework? Okay, so the 2 things you can do is you can start it. You can also, if you're running it locally on your computer, not using Sigmund or something, then you just type notebook, and it will, actually it pops up a web browser, and then you can type commands into the web browser. You can also, if you're online somewhere, you can type, I think this one's the better one to do. If you go to sagenv.com or .org, they're 2 separate servers actually. You can log in. You can also create an account by clicking here. You can just log in and then use Sage that way. And this doesn't
log in with the Sage password?
No, you make an account.
You just make an account.
No, I have an account already. But
right.
If you click sign up for a new Sage Notebook account, then it will ask you for your desired login and password, and then you type it in, and then you sign in with that login and password. And then you can use Sage online, just anywhere using a web browser. So here's an example of helping my wife with her biostats homework online. So, oops, it's not quite square. And have you ever used Google Documents? If you ever used that, this almost looks identical. It's very similar layout to Google Documents. So you can share worksheets with other people and publish worksheets so other people can look at them and so on. Okay, so back to the talk. So here's another example of the notebook doing a little bit of number theory. Here's an example of some of the range of things that Sage does. So just to give you a sense of the answer to the question, what is Sage? What it is, so we started with just this Python library, but then it very quickly became clear that it's a pain in the butt to install software. And especially with open source math software, which is what we're using to build Sage, it's often, I mean literally you could spend a week just trying to install one program because of the things it depends on. And installing all those dependencies can be hard. And unfortunately, so few people use math software, at least open source free math software, in comparison to the number of people that use, for example, Emacs or some like major program, that there just, in a lot of cases, aren't good ready-made solutions for installing many of these programs and libraries. In some cases there are, but in a lot of cases there aren't. So instead of making Sage this Python library that has dependencies that would require any very smart person 2 weeks of dedicated work to actually install, and I kid you not, I mean, maybe even worse, we decided to somehow try to do that once and for all, and then create a complete distribution of all the stuff that Sage depends on that you just build all at once. So, and then test it a huge amount on a lot of different machines and make sure that it would build in an automated way. So what Sage is currently is it's this tarball that you download. It's about 135 megabytes, I think. You extract it, you type one word, make, and then it'll sit there for about an hour and a half, and when that's done, it will have built every single thing you see listed here. And more. So basically it's all this stuff. So it builds it all, but in addition to building all this software in one sort of integrated way, and by the way, you don't have to build Sage from source. You can also download pre-built binaries, but at least you have the option of building any part of it or the whole thing from source, which is critical if you want to go in and change something. So for example, you might learn that there's an algorithm for computing something very relevant to some research you want to do that's implemented in the number theory library Harry. And you might want to say, okay, look at the code. You can do that. You can look at every line of the code that's relevant, but much more importantly, you can put little print statements in to get debugging information to see what it's doing, and then recompile that part, and then run your program and see exactly what it's doing, and make little changes, which is often important to be able to do. So anyways, this is a list of the various components of the system, but I should emphasize that in addition to all of this stuff, we've had to do a lot more than just put it all together in one package. We've written about, I think at this point, about 200,000 lines of new code that makes it so everything kind of works together in a unified way. Yes?
Is there like an extra zero on there? It seemed like it was like 20,000 lines of code like half a year ago or something.
It's 200,000.
I mean,
It's 189,000 unique
It's
lines.
like 20. So
I just checked it today. I mean, so this guy Mike,
it seems like it's grown a lot.
just to give you a sense of the speed, so a guy, Mike Hansen, who is an undergrad at Harding Mudd, who will actually give the Combinatorics seminar here in about 3 weeks, and if you meet him, tell him to come to grad school, because he's applying, and he might come. He spent the whole summer writing Combinatorics code. So he wrote this amazing C library for Combinatorics, wrote a bunch of other stuff, and just wrote, I think he submitted a patch and it was like 20,000 lines of new code that implements just a massive amount of Combinatorics. And he's, there's a lot of people that do that sort of thing. So the system is growing quickly with new code. So anyways, there's all this stuff for graphics, for group theory. There's a system called GAP which does group theory. There's a bunch of MATLAB-like functionality that's really pretty sophisticated. There are 3 libraries that are included in Sage: SciPy, NumPy, and GSL. And these are libraries that are used by a series of people doing supercomputing in numerical areas like computational chemistry and physics and so on. But they write their, especially these 2, are written in Python, so it's actually really easy to just include them in Sage. By really easy, I mean it took us months to get it all to build correctly, and on everything, there's issues with them requiring Fortran to build and so on, but we did get it to all work, and now it's included standard in Sage. And actually, one of the people that did most of the work on getting these included in Sage is Josh Cantor. He's one of the grad students here. So anyway, Sage can do a wide range of things. The one thing that you don't see really very clear here is statistics. There is some statistics functionality in SciPy. There's maybe 100 or so functions and various distributions if you do import scipy.stats, but it's not as comprehensive as of a stats package as what you'll get in something like R or Scata or something like that. So we need a little more statistics, I think. There's also convex optimization, which I didn't list here, but that's included in Sage. So it's definitely not just a number theory package. Another neat thing you can do with Sage is you can use other programs from within Sage. So if you wrote a program in Magma and you have Magma installed in your computer, you can call the functionality of that program from within Sage. So you can write a Sage program, and maybe one line will call out to Magma to do something, which in some cases that can be a great crutch before you get something working purely in Sage. You could say something about that, because You were in exactly that situation a few months ago.
Yeah, it was,
You at least were able to write the program.
yeah, I was trying to classify Eric Reckoned codes, and we had to use Magma because we didn't have an equivalence test. It was really annoying because that means you can only do it on one computer, and they were using Sage. So the quality is you can use like 50 computers.
Oh.
We couldn't.
We have a really neat distributed computation framework for Sage where it's kind of like SETI at home or something, where you can start a server, submit jobs to the server, and then start workers all over the place on different computers, and they just check with the server for a job, get the job, and then do it. And Robert's used that a lot in his research. I'm using it right now at this very moment to compute a bunch of Pekka eigenvalues. And interestingly, that distributed computation system was written by E. King, who's an undergrad here. And he put a lot of work into writing that. So let's see, next. So here are a couple of, so that was just an overview of Sage. There are a number of issues with Sage still, some serious problems. One is the size of the user base probably is less than 1,000, or it's very close to 1,000. So it would be much better if it were 100,000 users rather than 1,000. Then you kind of feel more that you're using something that's really, really serious. And I'd like it to be 100,000, but currently it's 1,000, probably. Maybe a little bigger, a little smaller. It's hard to tell. Every day there's always somebody new asking questions on the list, and right now there are 203 people subscribed to the developer mailing list, about 180 or so to the support list. And not everybody's going to subscribe to a mailing list because there's issues of robustness. There are actually two we addressed a lot at a recent coding sprint. There were two specific issues with hitting Control-C and it not interrupting correctly that we actually fixed. So that is less a problem. In certain cases, Sage will be much slower than other programs. Like maybe Mathematica could compute symbolically some integral way faster or something like that. In some cases, Magma is definitely faster than Sage. And on the other hand, sometimes Sage is much faster than the other systems. It just varies a lot. And often, Sage will be slower because nobody's ever used the code that you're using. Just nobody ever bothered using it, and they didn't need it to be fast. So it's not fast yet. And there are too many bugs in Sage because it's only been around for less than 3 years. And with only 1,000 users, then it's harder to become aware of bugs. The more people that use Sage, the less bugs it will have, and the more bugs it will know that it has, but the less bugs it will actually have because of them reporting them. Okay, so actually almost done. This is a short talk. Here's an example of sort of nice illustration of how Sage development often works. So I was reading through the Mathematica tour, and one of the first things they do in there, I think on page 6, is they say that Mathematica computes the number of partitions of 1 billion in a few seconds, a frontier number theory calculation. So I thought, wow, I have Sage with Perry in it, and I'm a number theorist, so I should be able to do a frontier number theory calculation. Even though I never actually tried to compute the number of partitions personally. And then I looked in the code actually in Sage and in Magma for that matter, and in GAP, and every open source program in existence would take years to do that calculation. So I just posted that statement on the Sage developer mailing list, and then there were about 72 replies by 15 different people with all kinds of ideas and suggestions of improvement. I didn't write a single line of code, but this guy at University of Michigan, John Mauber, who's a grad student there, and I don't think he's a number theorist. So he wrote some code based on a lot of the other discussion, and he wrote something that on my laptop right now will compute the number of partitions of that thing in seconds, namely 67.56 seconds. And if you time the latest versions of Mathematica, they take at least 10 to 15% more time. So in fact now Sage is faster at that particular calculation. And this sort of thing happens often. Another illustration, Bill Hart, who I mentioned earlier in connection with being on the job market, he wrote code for Sage that will do polynomial arithmetic, in other words, arithmetic in z adjoin x, faster than any other program in the world. Substantially, it's in a lot of cases in like everyday situations, 20 times faster than the fastest open source program. And it's 2 to 3 times faster than Magma across the board. And Magma is by far the fastest, way faster than those systems. So it's really cool. It's not the default in Sage right now though, because he's implemented basically multiplication and addition and nothing else. So it's not sort of ready for prime time. Okay, so here are some advantages, and then I'll end with this. So it's the only serious general-purpose math software that uses a mainstream programming language. All the other ones invent their own. Magma has its own language that's just for Magma. Mathematica has their own funny language, which is really powerful for certain things in mathematics, and amazingly powerful for certain things, but it wouldn't be the language you'd want to write a web server in or something. Whereas Python, you can actually write a really good web server in Python. People have done that. Maple has its own language. Everything has its own language except Sage. Its language is essentially just Python, which is a standard mainstream language which can do a lot of things besides math. So if you want to combine math with something else, then Sage is a good place to be. You can use a whole bunch of other programs from Sage. And I think, kind of tautologically, it has more functionality out of the box than any other open source program. I don't know whether it has more than any closed source program. I haven't really decided. But it basically contains all the other open source programs except Octave. But it has similar functionality to Octave. So it has a very large developer base, and all the development's done in the open. Every bug, you can read about it, all the development discussions in the open, etc. So download it, compile it, use it, and use it. And I'll give you part 2 of this talk, which is about specifically using Sage in the context of this course at the beginning of class on Monday. Okay? So are there any questions? We're out of time, so I understand that. But if you have any quick questions, feel free to ask after class, informally.
I wasn't doubting this was 3,000. I was just thinking like,
Yeah,
it's 2. I think it was actually 20,000.
I don't think it's been that low for a long time, but yeah, I think it was under 100,000 at Sage Days too. It's kind of scary how quickly it grows.
I can't